Hello, welcome to this video. We're going to go ahead and calculate average rate of change, specifically looking at square root functions. And this is no different than what we've been doing with average rate of change. So let's go ahead and look at some problems. First thing I want to focus on is refreshing your memory on what average rate of change is. Average rate of change is also known as slope. What is the slope between two specific points? So if I'm asked to find the slope between a line that passes through 2 points here, I can go ahead and calculate, okay, what's the rise divided by the run? Rise, that's also known as delta y. Run, that's delta x. How are my y values changing? What's that value? Divided by the change in my x values. So we do have a formula here, y2 minus y1 over x2 minus x1, and we're just going to calculate the slope between these 2 points. So my first point, 128, that will be x1, y1. 452, this will be x2, y2. So those are 2 points. Okay, take a minute, go ahead, plug those values in, and let's see what you get. All right, hopefully you paused the video and tried that. If I just go ahead and substitute here, y2 is 52, y1 is 28, divided by x2 minus x1, that's 4 minus 1. So 52 minus 28, this gives us 24. And 4 minus 1 gives us 3. 24 over 3 is 8. So the slope of this line is 8. Okay, so we're going to go ahead and apply this knowledge directly to square root functions, and we'll look at a couple of different forms of a function. So average rate of change. Average rate of change is the average change between y values over each unit of x for a specific interval. The average rate of change for an interval, again, it corresponds to the slope of the line through the 2 points at the ends of the interval. So we're just finding the 2 points and we're calculating the slope, and that's what we're doing. So average rate of change formula is delta f of x over delta x. And some people freak out with function notation. If the function notation is confusing you, just remember that your f of x values are the same thing as your y values. So I can go ahead and I can calculate the change in f of x values. F of x2 minus f of x1, the function evaluated at those two x values, divided by the difference in our x values. All right, let's go ahead and look at our first example. So in this example, we're given a context as well as a graph. So I can have kind of a storyline and supported by some data points that correspond. So it says the shoulder height h in centimeters, units are very, very important, especially in context, of a particular elephant is modeled by the graph of the function below, where the age t is in years of the elephant. And they want us to include units in our final answer. So part A, it says approximate the average rate of change over the interval 0 to 20. Over the interval 0 to 20. So if you're thinking about this, here's our information in a graph. 0 is right here. So here's 0. Here's 20. So I want to calculate the average rate of change over that interval. Okay? I want to go ahead and find my points. They've given us the x values. 0, and 20. Those are your x values. So step 1, find the points. What are the 2 points that you're going to calculate the average rate of change between? So I have 0 and I have 20. So I need to know, okay, what is the output at 0? So it looks like this point right here. And we're asked to approximate it. So a guesstimate. I'll say 70. And this is in centimeters. And then at 20, the point is right here. And I'll say 245. Okay, so again, this is x1, so this must be y1. It's the y value at that x value. Okay, then this is x2, so the corresponding y value will be y2. Okay, after you have your points, you're just going to go ahead and calculate delta y over delta x. Right, so our y values, 245 minus 70 divided by 20 over 0. Okay, if you have a calculator, you can go ahead and compute that, or compute that by hand. You should receive 175 centimeters over 20 minus 0, that's 20 years, which is approximately 8.75 centimeters per year. Okay, so there is our average rate of change over that interval. Another example, part B. Now they ask us to approximate the average change in shoulder height of an elephant from 20 years to 40 years. Okay, so this time they don't give us the x values in interval notation, but they do in words, 20 to 40 years. So again, my points, step 1, my points are 20 years, which we just said that height, shoulder height of the elephant was 245 centimeters. And at 40 years, so here's 40, so that point is right there. Let's go ahead and say 290 centimeters. And again, I'm approximating. It looks like it's right before there. Okay, so I'm going to go ahead and calculate delta y over delta x. So y2 minus y1 over x2 minus x1. So that would be 290 minus 245 over 40 minus 20. So we get 45 divided by 20. Which is approximately 2.25 centimeters per year. All right, I do have a practice problem here for you in a second. So go ahead, please pause the video, and I want you to give this one a try. All right, hopefully you had a chance to go ahead and try this practice problem. Here is the solution. First, you had to find the points for 40 and 60 years. So 290, if you use that from our previous example, and then at 60 years, I went ahead and used 320. If you use 315, if you use 320, if you use 324, that's fine. You're going to be approximately, you'll be close to 1.5 if you did your calculations correct. So now that we have our points, we can go ahead and plug it in. the difference in our y values, so 320 minus 290, divided by our x values. So 60 minus 40 is 20. And we get approximately 1.5 centimeters per year. Ask yourself, did you use the units? Did you have centimeters per year? If not, make sure you use that. Units are important when we're dealing with context. And then again, too, some people ask, okay, like where do you even get these values? Again, you're just estimating the value of the point with your y-axis, right? So at 60, looks like it's right here. So that height would be approximately 320. All right, here is our next example. And we're given a table of values. So you'll see these problems in a couple of different ways. You'll see it with a table of values, or you'll see it with a graph, or you may even see it just with a function. So here they say the speed in miles per hour of a tsunami can be modeled by the function S of D is equal to 3.86 times the square root of D, where D is the average depth in feet of water over which the tsunami travels. Be sure to include units in your final answer. So another way that you may see this problem is just with a given function, and then you have to calculate the function values for your points. So for part A, they say make sure you complete the table for the given depth values. So that's already completed for you. You can go ahead and fill in this table. And then part B says approximate the average rate of change over the interval 1,000 to 2,000 depth of feet. So we were calculating the average speed of the tsunami. So step one, I'm going to find my points. Remember, these are your x values, x1 and x2. So at 1,000 feet of depth in the ocean, how fast is this tsunami traveling? Yeah, 122.1. And then at 2,000, this is tying back into that earthquake drill that we just did, right? If you're near water, there can be a tsunami. So this will help you calculate how fast that tsunami is coming at you so you can get out of there. You're like, man, I'm about to die by a tsunami. Let me do some math. Okay, so at 2,000, it's 172.6 miles per hour. That's kind of fast. It's a fast tsunami. Yeah. So we're going to go ahead and step two, I'm just going to calculate, okay, what is my average rate of change? So AROC is equal to, sometimes I mess this up, like where I plug in values, so I always like to write the formula. Y2 minus Y1 over X2 minus X1. If you misplace values, that's a great way to just straighten yourself out. So you can say, okay, what's my Y2? Well, Y2 is the second Y value, 172.6. Okay, what's my minus Y1? Well, my first Y value was 122.1. Okay, divided by X2, which is 2,000, minus, let's see if I have another, well, I guess I'll use that one. Okay, minus 1,000. So pretty straightforward. So it looks like 50.5 miles per hour. I'm going to include the units, miles per hour, over 1,000 feet. Okay, so we can go ahead and divide. And this is going to be approximately 0.0505 if I want to include everything, miles per hour All right, here's a practice problem. Please go ahead, pause the video, give this one a go. Okay, hopefully you gave that one a go. Here is the solution to the practice problem. So we're asked to calculate the average rate of change from 3,000 to 4,000 depth in feet. So I'm going to find those points. At 3,000, the speed of the tsunami is 211.4 miles per hour. And at 4,000 depth of feet, it is 244.1 miles per hour. So I'm just going to use those values. Subtract the difference in the y values. So 244.1 minus 211.4. And then 4,000 minus 3,000 gives you 1,000. So you can go ahead and calculate, and we get 0.03 miles per hour per feet. All right, here is another practice problem for you. Go ahead and calculate the average rate of change over the interval 0 to 40 for the velocity of a car per power. All right, here is the solution for the average rate of change from the interval 0 to 40. Again, you're approximating, so your point, the velocity for the vehicle may be different for 40 horsepower, but I selected 53 kilometers per hour. So it'd be 53 minus 0 over 40 minus 0. So that if we do 53 over 40 is 1.325. If you use something else like 52, that's completely okay. Just ask yourself, did you use units? Kilometers per hour divided by horsepower. All right, here is the last practice problem. Please pause the video, give this one a go. Okay, so hopefully you pause the video. Here is the solution. You should have gotten 0.1875 kilometers per hour over horsepower. All right, that's going to do it for this video. Thanks for watching. Hope you learned how to calculate the average rate of change, specifically for square root functions in graphical or tabular form. Peace.